In this video, we're going to use the graph of a function that we're given, and we're going to use that to graph the derivative of that function. When we talk about the derivative of a function, what we're talking about graphing is the different instantaneous rates of changes along the curvature of our original graph. From class, we've talked about how the instantaneous rate of change, we call that a different name. We call it the derivative. So what we're doing is we're going to look at different slopes or instantaneous rates of changes of our graph, of our original graph. And what we're going to do is as we go along the graph, we're going to make a graph of those slopes, and that's going to be what we call the graph of our derivative. What we're going to look at first is we see that at x equals -3 here, we have this questionable looking minimum, where in previous classes we would say, oh yeah, that's a minimum, and we'd move on. We know that talking about the derivative, at mins and maximums of our graphs, we know that the tangent line that we draw to a minimum or a maximum, what that is a horizontal tangent line, or a horizontal derivative. What that means is the derivative equals 0. But we see that at this value here, what this x equals -3 actually is what's called a cusp. And from class, we know that cusps, when we have those in the graph of a function, those are not differentiable. So what that means is the derivative at x equals -3 here, it's not going to exist. So when we graph our derivative, our value at -3 is actually not going to exist. It's going to do something different. So we're going to keep that in mind as we look and analyze our graph. But now that we've established that, let's look at everything to the left of -3. From the function that we were given, we see that they've plotted points for us, or they've made it just so that as we go further and further away from -3 here, we're going to still stay with a constant instantaneous rate of change, or a constant slope, constant derivative. All these mean the same thing. But to the left of -3, to the left of -3, and this is x equals -3, mind you, we have a -1 as our slope. Put slope in quotation marks, as we call it a lot of different things now. Let's also look at to the right of -3, to the right of x equals -3. We have the same situation going on in that our slope stays the same value, but in this case, to the right of x equals -3, we have a +1 as our quote-unquote slope. So using all this information, knowing that at x equals -3 we have a cusp that is not differentiable, meaning the derivative won't exist at that point, and everything else stays a constant, either -1 or +1, depending on what direction you have, let's go ahead and graph that. So everything to the right of -3, we're going to draw an open circle on -3 and extend to the right. We're going to have a +1 as our slope. So the derivative, what it's going to look like as a graph, is going to look like this. And then as we graph to the left of -3, again using an open hole to signify we don't have a value at -3, we're going to get a slope of -1, so that's what's going to be graphed here. And after we do that, we've arrived at our graph. It's really as simple as that. So looking back at this graph, which we claim to be the finished product, or our answer, or our graph of the derivative, what we have here is we say the derivative exists everywhere to the left of -3 and to the right of -3, but it does not exist at x equals -3, and that's because in our original function we have what's called a cusp, meaning the derivative doesn't exist, so we get this type of graph as our answer.